Imagine training a deep learning model, and it performs beautifully on your training data, but then it struggles significantly with new, unseen information. Or perhaps your model is too simple to capture any meaningful patterns at all, leaving it underperforming across the board. The regularization strength parameter, often referred to as alpha or lambda, directly influences a deep learning model's bias-variance trade-off by controlling the complexity of the learned function. This mechanism works by adding a penalty to the model's loss function based on the magnitude of its weights. When alpha is set to a high value, the penalty for large weights becomes substantial, compelling the model to use smaller weights. This effectively simplifies the model, making it less sensitive to noise and specific patterns in the training data, thereby reducing variance and combating overfitting. Conversely, a very low alpha value applies a minimal penalty, allowing weights to grow larger and enabling the model to capture more intricate details of the training data. While this can reduce bias, it also increases the model's susceptibility to noise, leading to higher variance and a greater risk of overfitting. To effectively determine the optimal alpha value for a deep learning model, practitioners typically employ systematic hyperparameter tuning techniques. This often involves training the model with various alpha values and evaluating its performance on a separate validation dataset. Methods like grid search, random search, or more advanced Bayesian optimization can automate this process, helping to pinpoint the alpha that strikes the best balance between underfitting and overfitting for a given problem. An interesting detail about L1 regularization, also known as lasso, is its tendency to drive some model weights exactly to zero, effectively performing automatic feature selection by eliminating less important features from the model. In contrast, L2 regularization, or ridge, tends to shrink all weights proportionally, resulting in a more diffuse distribution of smaller, non-zero weights across all features. Ultimately, a carefully chosen alpha value ensures that your deep learning model not only learns effectively from the training data but also generalizes well to new, previously unseen data, allowing it to perform robustly in real-world applications.